Hello student, I am Professor Jayanta Chopre, working in Electronics and Telecommunication Department. I would like to welcome to this lecture on application of the Laplace transform. Now in previous lecture, we studied the inverse Laplace transform and how to find out the inverse Laplace transform using the partial fraction expansion. And in that, we discussed the three cases. First, when the roots are simple, means poles are simple. Case 2, when poles are repeated poles. And the third one is the complex pole. Now in this lecture, we are going to study the application of the Laplace transform. And in that, first, the solution of the differential equation using this transform, and second one is the analysis of the electrical networks using this transform. Now first we will see the first application, that is the solution of the differential equation using the Laplace transform. Now we studied the classical method to solve the differential equation in mathematics. And in case of the classical method, first you have to identify whether this equation is homogeneous equation, non-homogeneous equation, which types of equation is this one. Then after that, to obtain the solution of the differential equation, you have to find out the complementary function CF and the particular integral. And the response or the solution of the differential equation using the classical method is the addition of the complementary function and the particular integral. And this particular integral is different for the homogeneous equation and for the non-homogeneous equation. Hence this method is somewhat difficult, or it takes time. This is the tedious method. Hence instead of that, we can easily solve the differential equation using the Laplace transform, and automatically we will substitute the initial conditions. And this is the beauty of the Laplace transform. Then here the total response of the differential equation, or the total response of the system, because the system is represented in terms of the differential equation, is nothing but the natural response. That natural response is occur due to the initial condition. And second one is the force response, and the force response is due to the input or the excitation given to that system. And when the initial conditions are 0, then the total response that equal to the force response that is due to the input. Now to solve this differential equation, we know the differential equation is like the d2 xt or yt here. Or if this is output, dt plus 3 dy by dt plus 2 yt, that equal to something x of t, like this. Mean this is the differentiation in time domain. Hence here we will use the differentiation theorem, that is differentiation in time domain. And we know that this Laplace transform of the differentiation of single differentiation of x of t, that equal to s x of s minus this initial value. And here meaning of this, we are adding the 0 in this system. S is in numerator. Similarly, the Laplace transform of the double differentiation d2 upon dt square xt, that equal to s square x of s minus this s x of 0 minus dx 0 minus dt. Now we discussed this property while studying the properties of the Laplace transform. Now, here we will consider one example that will clear how to solve the differential equation. This is the second order system. This is the xt input and this is the output, and the output and input is related using the differential equation. This is mathematical modeling of this system. Now first we will consider all the initial conditions are 0, and using that we will solve this differential equation, that is d2yt upon dt square, this plus 3dyt. Now we will take the first step is take the Laplace transform of this given differential equation. The Laplace transform of d2yt upon dt square into 3 dyt by dt plus 2yt, that equal to the Laplace transform of the x of t. Now here we will consider this x of t equal to impulse function. Then what is the Laplace transform of this? In previous slide we know that the Laplace transform of this d2 upon dt square xt equal to s square x of s. Now here instead of xt this is yt, and so we will write here this is s square y of s minus s into y0 minus dy0 upon dt. This is the Laplace transform of this term plus the Laplace transform of the second term 3 into s x of s minus s y of s minus s y0 minus, and what is Laplace transform is 2ys, that equal to x of s, and Laplace transform of the impulse function, that equal to 1. Hence x of s is 1 because this is the impulse function. X of t is del t, and so as the initial conditions are 0, means the second term, this term, third term of this first bracket, and for the second bracket, the second term, this term becomes 0, and as initial conditions are 0, we will write this is s y of s plus 3 s y of s plus 2 y of s, that equal to 1, as x of s is 1, means we will write this as y of s, take y of s common, this is s square plus 3s plus 2, that equal to 1, means y of s, that equal to 1 divided by s square plus 3s plus 2. Now find out the factor of this, means poles of this system. This is s 2 1s are 2, means factor for this 1 upon s plus 1 plus 1 upon s plus 2. Now here the roots or the poles are the distinct, are the simple 1 and 2. As we will say, this is C1 s plus 1 residues plus C2 s plus 2. Now find out the residue C1 equal to y of s into s plus 1 and substitute s equal to minus 1. After this we are getting this is s plus 1, this is s plus 2, because we will rewrite this equation as 1 upon s1 s plus 1 into s plus 2, as these are the root of this, multiplied by s plus 1 and substitute s equal to minus 1, and after solving this c1 is 1. Similarly the c2, this equal to y of s into s plus 2 and substitute s equal to minus 2. Now y of s is 1 upon s plus 1 into s plus 2 into s plus 2 and substitute s equal to minus 2, with this equal to minus 1. If you substitute minus 2, this becomes minus 1. Means c1 is 1 and c2 is minus 1. Now substitute this value in equation 1, means the equation 1 becomes 1 divided by s plus 1 minus 1 divided by s plus 2. Now take the inverse Laplace to obtain the solution in time domain. Yt equal to Laplace inverse of y of s, means the Laplace inverse of y of s, that equal to e raised to, this is minus t and minus e raised to minus 2t. This is yt equal to e raised to minus t minus e raised to minus 2t. Now this is the solution of this differential equation. The differential equation considering the initial conditions, all initial conditions are 0. Then next one is, let consider the initial conditions are not 0 and that initial conditions are given, and that equal to 1, means y of 0 equal to 1 and the differentiation of this y of 0, this value is also 1. Now the same problem, the d2yt upon dt square plus 3dyt upon dt plus 2yt, that equal to xt, and here we will consider the xt, that equal to impulse signal or impulse function. I mean, this is the this previous was the response for the impulse signal. Then take the Laplace transform of this. The Laplace transform of this is d2yt upon dt square plus 3dyt upon dt plus 2yt, this equal to Laplace transform of x of t. The Laplace transform of this first term is s square y of s minus s y0 minus dy0 upon dt plus 3 into s y of s minus this is y of 0 plus 2ys, that equal to x of s. Now simplify this and substitute the initial condition. Put initial condition or the value for this. This is s square y of s minus s into 1 minus 1 plus 3 s y of s, multiply this 3 minus this 3 into 1 means this is 3 plus 2 y of s that equal to x of s. After simplifying this is s square y of s minus 1 plus 3 s y of s plus 2 y of s that equal to x of s, and x of s is 1. Then we will write, or we will simplify the equation as y of s that equal to, take the common, this y of s, keep all this term of the y of s to the left hand side and remaining terms to the right hand side, and taking this we are and take the y of s common, then this is s square plus 3s plus 2, and that equal to x of s plus x of s plus s plus 1 s plus 1, and x of s is 1, this minus 3, again this minus 3 is, this term is present, this minus s minus 1 this term, and this is minus 3, after this is x of s, this is minus 3, this become plus 3, means this is x of s plus s plus 4, and x of s is 1. Here we are getting these two terms, y of s that equal to s plus 4 divided by s square plus 3s plus 2 plus x of s divided by s square plus 3s plus 2. Now here the first term is due to the initial condition, and this is called as the natural response, and this is due to the input, and this is called as the force response, and the total response of this system is nothing but the natural response plus the force response. Now we will simplify this, s plus 4 plus this is 1, x of s is 1 divided by s square plus 3s plus 2 is s plus 5, or we will find out this response separately, the natural response and the force response. And for the natural response, if we say this is the y1 s and this is y2 s, and at last we will add all these two response, this is s plus 4 divided by s plus 1 into s plus 2 plus 1 divided by s plus 1 into s plus 2. Now expand this equation using the partial fraction expansion. This is c1 divided by s plus 1 plus c2 divided by s plus 2 plus c3, or directly we will write this as 1 upon s plus 1 minus 1 upon s plus 2, or you can find out the c3 and c4. Now if we write this above equation like this become s plus 2 minus s minus 1 divided by this term. This plus s minus s will be cancelled and this is 1. Mean this is 1 divided by this. Then find out C1. What is C1? C1 is y1s, mean this, into s plus 1 and substitute s equal to minus 1. And after substituting this, we are getting this C1 that equal to 3 and C2 equal to minus 2. Means y of s that equal to 3 divided by s plus 1 minus 2 divided by s plus 2 plus 1 upon s plus 1 minus 1 upon s plus 2. And if we take the inverse Laplace of this, then we are getting a time domain solution. Take the Laplace inverse of the y of s, that is 3e raised to minus t minus 2e raised to minus 2t. Now this is the response due to the initial condition. I mean this is the natural response in time domain, plus e raised to minus t minus e raised to minus 2t, and the second is the response due to the input signal, and hence this is called as the forced response and this is called as the natural response. And the total response y of t, the total response is natural response plus the forced response, and that equal to, if we this minus 2, this 3 and this 3 and this 4 1, that become 4 e raised to minus t, and this minus 3 e raised to minus 2t. In the output or the total response of the system is the natural response plus forced response, and that equal to this. Then the representation of the system. Now there are two methods to represent the system. One is the using the differential equation, mean the output and the input is related in terms of the differential equation, and second one is the finding the transfer function, and the transfer function is nothing but this is system output divided by input. If y of s is the output, x of s is the input, then y of s divided by x of s. Means this is the two polynomial in numerator and in denominator, and this is called as the transfer function. Means system is represent in two ways. First one is writing a differential equation or relating the input and the output with differential equation, that is mathematical equation, and that is called as the modeling of the system. And second one is finding the transfer function, that is the ratio of the output or the response of the system divided by input, or called as the excitation of the system. Now in this case we are getting these two polynomial, one polynomial in denominator and second one is in numerator. This is in numerator, this one is in denominator. Now for proper transfer function, the m should be less than or equal to n, where m is the order of numerator. Means if this one is s plus 1 divided by s square plus 2s plus 3 like this, this is the ratio, this is transfer function, ratio of this numerator and denominator, where this m means here raised to 1 or s raised to m divided by s raised to n. M is the order of numerator and this is the order of denominator. And for the proper transfer function, this m should be less than or equal to n. If m is greater than n, means the order of this numerator becomes greater than the denominator, then this is not proper transfer function. Now this is the example 1, and in this example we have to plot the pole 0 diagram of this given transfer function. As we know that the S is the complex plane, along the x-axis the convergence factor is there, and that convergence factor is denoted by the sigma. Means along this x-axis sigma is there, and along this y-axis the imaginary part, that is the j omega, is there. Now to represent the pole 0, we will first find out the root of the numerator and the root of the denominator. Root of the numerator is nothing but the 0 of the system. Means this is the critical frequency at which the transfer function becomes 0. Or we will find out the value for this S, so that the transfer function becomes 0, is called as the 0 of the system. And in denominator we will find out the root at which the transfer function becomes infinity, that is called as the poles of that system. Now first find out this root, the 0, here this s plus 2 equal to 0, this numerator for this first problem, means 0, for 0 means z1 is at s equal to minus 2. And to find out the pole, we have to solve this equation, this polynomial equation, is in quadratic method. This quadratic equation is minus b plus minus square root of b square minus 4ac divided by 2a. If the equation is a square plus bs plus c. Here a is the coefficient of s square, b is the coefficient of s, and c is the constant. Then for this equation, s square plus 2s plus 2, for this equation, find out the roots. Minus 2 plus minus b square means 4 minus 4ac, this is 8 divided by 2. We will write this is minus 2 plus minus, this is square root of minus 4 divided by 2, and that equal to, we will write this is minus 2 plus minus square root of 4 is 2, and this is square root of minus 1, and this square root of minus 1 is j, plus minus j. Here this one is j, means this become plus minus j. This is minus 2 plus minus 2j divided by 2. This is complex root. Then this become minus 1 plus minus j. Means two poles are there. One pole is at minus 1 plus j, minus 1 plus j, and second pole is minus 1 minus j. Now we will plot the pole 0 diagram for this. This is sigma, this is the complex plane, S plane. This one is j omega. This is 0. Along this x-axis, this is real part, and along this y-axis, imaginary part. This is j1, j2, minus j1, minus j2, minus 1, minus 2, minus 3. Now first 0 is at sigma equal to minus 2, means this is the 0, and the 0 is represented by this symbol. And there are two poles, and that two poles are the complex conjugate of each other. Means the real part is minus 1 and imaginary part is plus j1, and this is minus j1. Means these are the two poles of this given transfer function or given this system. Similarly, you can draw the pole zero diagram for this system. Then next problem, obtain the transfer function of the system if y of t is given this and x of t is this one. How will find out the transfer function? The transfer function that equal to y of s divided by x of s. Means find out the Laplace transform of y of t that equal to y of s. And the Laplace transform of e raised to minus t minus 2 e raised to minus 2t plus e raised to minus 3t. First find out y of s that equal to 1 upon s plus 1 minus 2 upon s plus 2 plus 1 upon s plus 3. Solve this y of s that equal to the LCM for this is the product of these three terms. The first term, the second term and this third term. Means y of s that equal to this is s plus 2 into s plus 3 minus 2 s plus 1 into s plus 3, and for this the remaining these two terms 1 into s plus 1 into s plus 2 divided by this s plus 1 s plus 2 s plus 3. Now simplify this. This is s square plus 5s plus 6. Expand this two term, multiply s square 3s, this 2s means 5s, and last term multiplication of 6 minus 2 expansion of this s square plus 4s plus 3 plus expansion of this last two terms s square plus 3s plus 2 divided by this. Then simplify this, multiply this minus 2, and after this we are getting this is s square plus 5s plus 6 minus 2s square minus 8s minus 6 plus s square plus 3s plus 2 divided by s plus 1 s plus 2 s plus 3, and that equal to y of s. Now this s square and this s square that become 2s square plus 5s 3s means this is 8s, and this is 6 minus 6 0, this plus 2, then this minus 2s square and minus 8s divided by s plus 1 s plus 2 s plus 3. This will cancel out, and only in numerator we are getting 2 divided by s plus 1 s plus 2 s plus 3. This is y of s. Similarly, find out the x of s. X of s is 1 upon s plus 0.5 e raised to 0.5 t. Hence y of s divided by x of s that equal to 2 divided by s plus 1 s plus 2 s plus 3 divided by 1 upon s plus 0.5 as x of t that equal to e raised to minus 0.5 t. Here x of s is 1 upon s plus 0.5. This is 2 divided by the denominator term multiplied by this s plus 0.5. Means the transfer function or the answer for this is 2 into s plus 0.5 divided by s plus 1, s plus 2, s plus 3. Then this is the example 3. Find out this Laplace or solve the differential equation using the Laplace transform method. And the differential equation for the initial conditions are given. And the input is given, means we are getting the two responses. First one is due to the natural and due to the forced response. And the x of t input is this is exponential signal. Now we will solve this. First step is take the Laplace transform of this Laplace transform of the d2yt upon dt square. Take the Laplace transform plus 3 dyt plus 2yt. This equal to Laplace transform of the input. This is the differential equation is same. Only the input is changed and the input is differentiation of the xt, and the xt signal is e raised to minus t. Instead of impulse, this is the e raised to exponential signal x of t. Take the Laplace transform, that is s square y of s minus s into y of 0 minus dy0 upon dt. This is the Laplace transform of this first term. The Laplace transform of the second term is s y of s minus y of 0 minus plus 2y of s this is the third term, and that equal to s x of s minus initial condition for the xt, but this is not given, means we will consider this 0. Now we will substitute the initial condition s y of s minus s y of 0 is 2, means multiplied by 2 minus 1 plus 3 into s y of s minus 2 plus 2 y of s, and as this x of 0 is not given, means we will consider this as 0. This equal to s x of s. Then simplify this equation. For y of s, next one is we will keep this y of s on the left hand side and all the remaining term to the right hand side, and after simplifying this equation we will write this is y of s, this equal to s square plus 3s plus 2, this equal to s divided by s plus 1 plus 2s plus 7. Now see here, this 2s plus 7 means this is minus 6 and this minus 6 and this is minus 1, means this is minus 7, and on right hand side it become plus 7 and the minus 2s become plus 2s. Now simplify the right hand side. Take LCM is s plus 1, means this is s plus 2s plus 7 into s plus 1 divided by s plus 1, and expand this term and solve this term. After expanding and solving this, we are getting to this 2s square plus 10s, or we will solve this. This is s plus 2s square plus 2s plus 7s plus 7 divided by s plus 1, and that becomes 2s square 7, 8, 9, 10 plus 10s plus 7 divided by s plus 1. Then we will write this y of s, that equal to 2s square plus 10s plus 7 divided by s plus 1 divided by s square plus 3s plus 2. Now find out the fraction roots of this. I mean, this is 2, 1. Means we write this is 2s square plus 10s plus 7 divided by s plus 1 and s plus 1 into s plus 2, and this is s2s square plus 10s plus 7 divided by s plus 1 square into s plus 2. Now expand this using the partial fraction expansion, that is c11, as this is multiple root square plus c12 s plus 1 square plus c1 s plus 2. Now first we will find out the c1 and c12. c1, that equal to the y of s is 10s plus 7 divided by s plus 1 square into s plus 2, and substitute multiplied by s plus 2 and substitute s equal to minus 2. This will cancel out, and if we substitute s equal to minus 2, we are getting this c1 is minus 5. Similarly, c2 is 2s square, that is y of s is y of s, and multiplied by s plus 1 whole square and substitute s equal to minus 1. This is cancel out, and if we substitute this is minus 1, then we are getting this value is minus 1. Then find out this is c11, this is c1, this is c21, c12. Then find out c11. Now for this, if you observe this equation, this is L is 2, I is 1, means 2 minus 1. We will find out this 1 upon 2 minus 1 factorial, and differentiation of 2 minus 1 means one single differentiation, and this is 2s square plus 10s plus 7 divided by s plus 1, that is y of s, and multiplied by s plus 1 square, and substitute s equal to minus 1. This is cancel out, and this is differentiation of u by v, means v into differentiation of u minus u into differentiation of v divided by v square, means c11, that equal to s plus 2 into differentiation of this term is 4s plus 10 minus u is this term 2s square plus 10s plus 7, and the differentiation of this is 2 divided by s plus 2 whole square. Now substitute here s equal to minus 1, and after substituting s equal to minus 1 we are getting this c11 is 7, means we will write this y of s that equal to 7 divided by s plus 1 minus 1 divided by s plus 1 square minus 5 divided by s plus 2. Now take the Laplace inverse y of t that equal to Laplace inverse of y of s. And that becomes y of s, this is 7 e raised to minus t e raised to minus 2t minus 5 e raised to minus 2t, and this is y of t. This is the solution of the differential equation for the given initial condition. Now second application is the analysis of the electrical network using the Laplace transform. Now mainly the electrical network is consist of RLC, and if we apply the Kirchhoff's voltage law, that time we are getting the integral differential equation. Then we will convert that integral differential equation into the differential equation. Integral differential equation means the equation which consists of the integration terms and the differentiation term. And then the differential equation is analyzed using this Laplace transform method. This is the first method to analyze any electrical network. Also there is the second method to analyze this electrical network. Now in second method, each element in the circuit is replaced into its S domain, considering the energy stored in the inductor and in the capacitor. Second, once we convert this all these element into the Laplace transform or the in S domain, also initial energy in L and C is taken into account by adding independent source in series or parallel with the element impedance. After that, use the Kirchhoff's voltage law or the current law, write down that equation, and that equation is algebraic equation, and then take the inverse Laplace to obtain the solution in time domain. Now the basic elements is RLC. Now equivalent element of the RLC in S domain or in Laplace domain. As we know that the resistors is not stored the energy, and the relation between the voltage and current for the resistors is Vt equal to Rit. This is linear relation. In the Laplace transform of this Vt, that equal to Laplace transform of this R into It, and that equal to Ris. Now this is the time domain representation of this resistors. This is I. Now this I is replaced by S, and this is Vs, and this is the S domain. Then second one is the for inductor. Now inductor and capacitor store the energy, and we know that the energy stored in case of the inductor is half Li square, and in case of capacitor half Cv square. And the inductor voltage and the current relationship is not linear, and that relation is VL equal to L di by dt. This is the differentiation in time domain. Now we have to convert this time domain into S domain and take the Laplace transform, and when we take the Laplace transform, the differentiation of the Laplace transform is this one. Means we will write this is SLIS minus LI0 minus. And the representation in time domain is like this. IT, this inductor. This is the initial current. This is the initial current. And this arrow is showing that the initial current is flowing through the inductor. And this is replaced in S domain like this. This is VS, IS, SL. This first term SL. And this is the initial, the voltage due to this initial current is LI0 minus. Second one is in terms of IS, we will represent this equation is like this in S domain, and the representation is shown in this figure B. In case of the inductor, current flowing to the inductor is not suddenly changed. Hence, when there is the switching action, that time IL0 minus that equal to IL0 plus. Similarly, for the capacitor, the voltage equal to 1 by C integration of minus infinity to t it dt, that equal to 1 by C 0 to t it dt plus this initial voltage. Means V of S equal to 1 upon SC I of S plus VC 0 minus. Here we are using the integration property. We know that if there is the integration in the time domain, then divide by S. This is 1 upon SC I of S. And the representation of this capacitor in S domain is like this. This is the initial voltage. This is in time domain. This is added, this voltage. This is plus minus V0 divided by S. And this is constant. And the constant of the Laplace is that constant divided by S upon 1 upon SC, and this is IS. And in terms of IS, the representation is like this. This is the equation IS, that is current flowing through the capacitor. This is the voltage across this capacitor. And the capacitor stores the energy in terms of the electrical energy, and the charge or the voltage across this capacitor is not suddenly changed. Hence, this voltage across this capacitor before switching and the after switching is same. Similarly, current flowing through the inductor before switching and the after switching is same. And this is called the initial conditions. If there is the switching action at t equal to 0, then we will say that I0 minus is current flowing through this inductor prior to switching action, and I0 plus is just after switching. Similarly, for this capacitor, the voltage is prior to switching, voltage across that capacitor, and the voltage across that capacitor VC 0 plus is the after switching. Now we will solve this problem, or we will analyze this problem using the Laplace transform method. This is electrical problem. The resistance value is 1, L is 10, and the voltage is V. And we have to find out this IT. Now, first method, you write down this differential equation and take the Laplace of this, or otherwise you can directly transform this equation into the S domain and write down the algebraic equation and solve this. Now, if we write this Kirchhoff's voltage law for this equation, for this circuit, Kirchhoff's voltage law, or for this loop, then RIT apply KVL R into IT plus L di by dt, that equal to V. Now take the Laplace of this RIT plus L di by dt, that equal to Laplace of this. And the Laplace of this in resistor, we know that this is R into Is plus this is S L Is minus L into initial current, but the initial current is not given, hence we will consider this initial current is 0, or otherwise we will find out this, and that equal to, this is constant voltage, hence this Laplace of this V by S. So we solve, this is Is, that equal to, take Is common, this is R plus S L, this is 0, that equal to V by S. So we write this is I of S, that equal to V by S, and this common is S L plus R. Then solve this, V divided by S, take L common, that is S plus R by L into L, that equal to V by L divided by S, S plus R by L. Now there are two roots of this denominator, means there are two poles, one is at S equal to 0 and second one is at S equal to minus R by L. Now solve this equation using the partial fraction expansion, this C1 upon S plus C2 S plus R by 2. Now first find out the residues. Here C1, that equal to V by L divided by S, S plus R by L into S, and substitute S equal to 0. And if we substitute S equal to 0, that is V by L divided by R by L, means this LL will cancel out, and that is V by R. Similarly, find out C2. C2 is V by L divided by S, S plus R by L into S into S plus R by L, and substitute S equal to minus R by L. This will cancel out, V by L into L by R, and this is minus, this L cancel out, that is minus V by R. Now we will substitute this residues value in equation 1, and then we are getting this equation I of S, that equal to V by R S minus V by R e raised to, this is in S domain, S plus R by L. Now to obtain this current, we have to find out the current flowing through this circuit, or we have to analyze this circuit. Then to find out this current IT, we have to take the Laplace inverse of I of S, and that equal to Laplace inverse of this ut, Laplace of this 1 by S, and the Laplace inverse of this ut. Ut is 1 in a step function, means this is V by R minus V by R e raised to minus t. So we will write this I of t, current flowing through this inductor and this capacitor network, inductor and resistor network is V by R 1 minus e raised to minus t ut. Now the second problem, in this network shown in figure, the switch K is moved from position A to position B at t equal to 0. Means switch is changed at t equal to 0 to position B, and steady state existing in the previous before t equal to 0. Means for a long time the switch is connected to this position A. Solve this current IT using this Laplace transform method. Means we have to find out this current IT when switch is at position find out IT when switch is at position B. Now when switch is at position B, that time the equivalent circuit is like this. This is capacitor and this is inductor C and this is L, and apply the Kirchhoff's to find out this current. Apply the Kirchhoff's current law for this, that is 1 by C integration of IT dt plus L di by dt that equal to 0. Take the Laplace of this 1 upon SC I of S plus V0 minus divided by S plus SL I of S minus L into I0 minus. Now when the switch was at position A, that time the equivalent circuit was like this. And there is no capacitor is connected, means the initial charge on this capacitor is 0. This term is 0. But this inductor is connected in this circuit when this switch was at position A, and the equivalent circuit is this. Now here we have to find out the initial current, and we know that this just before switching, means prior to switching, and after switching the current through the inductor remains same. Now for a long time, a steady state, means steady state condition is established when the switch was at position A. Now in that case, the current flowing through this L becomes constant, and that current is constant, I is constant. Now what is V? V equal to L di by dt. As I is constant, means the di, this V becomes 0 because L into differentiation of constant. Means the inductor acts as a short circuit when time t equal to infinity, or as this is connected for a long time. Now what is this initial current? Now the initial current flowing through this inductor, this is voltage, this is R, this is short circuit, means the initial current that equal to V by R. And for the inductor, as current is not suddenly changed, we will say that I0 minus that equal to I0 plus that equal to V by R. Now the switch is moved from position A to position B, and that time this current becomes IL 0 plus. Now substitute this initial current. After substituting this initial current, we will write this I of S that equal to 1 upon SC I of S 1 upon, or we will write this 1 upon SC I of S plus SL I of S. Now this term is 0, right? We have written this term as well as this term, and this IL 0 minus this become V by R, means this is minus L V by R that equal to 0. Take IS common, in 1 upon SC plus SL that equal to L by R into V I of S that equal to, or we will solve here, this is 1 plus S square LC divided by SC. Take LCM is equal to VL by R. Yes, I of S that equal to VL by R into SC divided by 1 plus S square LC. Now take LC common, VL into SC divided by R into LC common, 1 upon LC plus S square. This L cancel out, this C is cancel out, and this equal to V by R, this is S square plus 1 upon root LC, and here this is S. And we know that the Laplace of cos of omega t that equal to S divided by S square plus omega square. Mean this is S square, this is omega square, and this is S. Means this V by R cos of 1 upon root LC into T. I of T that equal to V by R cos of 1 upon root LCT. Now these are the assignment question. You solve these questions. Now in this lecture we studied the application of the Laplace transform, how to solve the differential equation using the Laplace transform, and how to analyze the electrical circuit using the Laplace transform. Okay, we stop here.